Picking up with where we left off at the end of section 3.1, we have another scenario where we have a sample percentage, the 51%, and we want to know how accurate that would be with respect to all adults nationwide rather than just the ones in the sample. At this point, about all we could say is that the population percentage should be close to 51%, but we can do better than that if we have an interval estimate instead of just a point estimate. So an interval estimate gives a range of plausible values for a parameter, and it incorporates the point estimate. If you look at the common form, the statistic is the point estimate, and it would be that plus or minus the margin of error to end up with an interval estimate. The margin of error is a new concept. That's not what showed up in section 3.1. In section 3.1, we had the standard error. The standard error is part of the computation to get a margin of error. That will show up later in this section. But the reason we're starting here is because this is the simplest computation for getting a confidence interval if you already have the margin of error simplified. Later in the report about disaster preparation, it says that the margin of error is plus or minus 3 percentage points. So now getting the interval estimate is easy because we have the point estimate of 51%, we have the margin of error of 3%, 51 plus or minus 3 would give us the interval from 48% to 54%. So the conclusion is that the parameter, the percentage of all adults nationwide who believe that the country is just as vulnerable to the effects of natural disasters and other emergencies as it was prior to Hurricane Katrina, probably between 48% and 54%. We can't say anything definitive because we don't know what the parameter actually is. We don't know what the population percentage is. It's very likely that it's in there, but it's not 100% guaranteed. For another example, we have a random sample of 755 US cell phone users aged 18 and up. We have a sample mean of 41.5 text messages sent or received per day, margin of error of 12.2. And then if we want to give an interval estimate for the parameter, the mean number of text messages sent or received per day for all adult US cell phone users, we have the two pieces. This is pretty quick. 41.5 plus or minus 12.2, and you get the endpoints. I made the initial part in blue down toward the bottom a little bit more specific this time because we know what the statistic is. It's going to be a sample mean here. This is for a mean, not for a proportion. So the notation for a sample mean is x bar. I figured I might as well put that in there. Going back to this example from section 3.1 where we had the 4 polls about how to elect the president, if that should stay the same or if it should change or if somebody doesn't know. What we focused on before was that the percentages in the first row change. They're not the same in every sample. But look at the margin of error on the bottom. That changes too. And why does the CBS poll have the smallest margin of error? Same reason that the Marist one has the biggest. It has to do with sample size. So the larger your sample size is, the smaller your margin of error. And this goes along with what was there at the end of section 3.1, where generally if you have a larger sample size, you're going to have a more precise estimate. Quantitatively, what that means is that you'll have a smaller margin of error, so you'll have a narrower interval. In a quantitative sense, that would be the thing that's more precise, would be to have a narrower interval. And certainly based on what's there, we could construct confidence intervals, so we'll do it for the first two, for the USA Today sample and the CBS News sample. It's generally better to write these as proportions rather than percents, so that's why I did all those conversions. And the thing to notice here is that there's no way that the parameter is contained in both intervals because they don't overlap. And it's entirely possible that the parameter could be in neither interval. It could be between 0.451 and 0.512. That's why I put these two in here to kind of illustrate that it's certainly possible for your interval to miss the parameter. At least one of these has to miss it since there's no overlap. By definition, a confidence interval is computed from sample data in a way that will capture the parameter for a specified percentage or a specified proportion of all possible samples. And that specified percentage or specified proportion is called the confidence level. What we're going to deal with in this section is going to be just 95% confidence because there's a shortcut for that. So that's why that's the one at the bottom. That's why that third point says for a 95% confidence interval, that's going to contain the parameter of 95% of all possible samples. You can have different confidence levels, though. You can have 90%, 99%. Those are the other two that are sort of common. Once in a while, you see 98. So a 90% confidence interval would contain the parameter for 90% of all possible samples, and so forth. Those other confidence levels are going to show up in section 3.4. So we're going to do them. We're just not going to do them yet. The sentences on this side look simple, and they're not. Conceptually, they're actually pretty hard. Because the way that this works is, in a way, the reverse of the way that things work in algebra. Because in algebra, the numerical terms are your constants, and then the unknown is the variable. Here it's kind of the other way around, because the parameter is the thing that's unknown for us when we're estimating one. Right? When we're computing a confidence interval, it's because you don't know the parameter. If you did, there would be no point in constructing a confidence interval. So the parameter is the unknown, but it's fixed. It has a numerical value, and you just don't know what it is. So when you estimate a parameter, really you're doing it at a specific point in time. So if you're at a specific point in time, a fixed point in time, then the population is fixed, so any population measure would be fixed as well. However, the statistic, which would be the thing that you actually have a numerical value for, that's random because it's based on the sample. If your sample is being randomly selected, then any measure associated with that, that's going to be random as well. But the interval is based on the statistic because of the idea of statistic plus or minus margin of error. So the statistic is effectively its midpoint. The interval is going to be random too. So since you have a random sample, that leads to a random statistic, which leads to a random interval. The thing that varies if you had a whole bunch of samples won't be the parameter. It'll be the statistic and then consequently the interval. And that's what that picture is supposed to signify. What's going on in this picture? The vertical line in the center, the vertical black line, is supposed to represent the parameter. And those line segments, both colors, the green ones and the red ones, are supposed to represent confidence intervals. So for each line segment, the circle in the center is supposed to represent the point estimate, and then the segment itself is the interval, so the ends of the segment would be the endpoints. And then the ones that are green are ones that capture the parameter. The way that's supposed to be shown pictorially is that they overlap that center line. But the red ones don't. So those four on the right and the one on the left is really close. The idea is that those five that are red don't capture the parameter because they don't overlap that vertical black center line. 95% of all 95% confidence intervals will capture the parameter. However, 5% won't. And those red ones are supposed to symbolize the ones that don't. Here is where the standard error appears. If you want to estimate a 95% confidence interval, as long as your sampling distribution is relatively symmetric and bell-shaped, you can do it like this, where you could compute the margin of error as 2 times the standard error. The reason that works goes back to the 95% rule in Chapter 2, the idea that if you have an approximately bell-shaped distribution, about 95% of the data should fall within 2 standard deviations of the mean. That 2 standard deviations of the mean part, that's where that 2 is coming from in that formula. This shortcut is only going to work for 95% confidence. It won't work for any other confidence level, but that's why this is the starting point, because there is a shortcut that's fairly straightforward that we can work with. Here's an example where we can use that formula. Notice that in that first bullet point, the way that I have that written is inconsistent. That's on purpose, where the point estimate is written as a percentage, but the standard error is written as a proportion. Here, you just have to convert everything to make sure you have the same units, and it would be better generally to do it with proportions, not with percentages. So if we're going to find a 95% confidence interval for P, the proportion of all American cigarette smokers who smoke at least a pack a day, there it is. I converted the 26% to 0.26, but then it's going to be 0.26 plus or minus 2 times 0.034, 2 algebraic steps, multiply, then plus or minus, following the order of operations, and you end up with the endpoints on the right, 0.192 and 0.328. So far, computing the confidence interval isn't anything too crazy, but the interpretation is going to be a little tougher. This first part at the beginning about 95% confident, this idea of since 95% of all samples yield intervals that contain the parameter, we'd say that we're 95% confident that our one interval contains the parameter, since we're only going to have one in practice. The interpretation of a confidence interval, you need 3 things. You need the confidence level, which is the 95% part. You need the endpoints of the interval, which that part kind of goes without saying. If you're interpreting the interval, you need the interval itself. The other part that you need, and this is the hard part, is to write out the parameter. When you're writing out the parameter, you got to have 3 things. The type of number, really that's saying, is it a proportion? Is it a mean? That's what I mean by type of number. Whatever the population is has to go in there. And then there's a specification part. So Without specification, let's say that you're trying to estimate some proportion that relates to all adults in the US. So you'd say something like, we're 95% confident that the proportion of all adults in the US is between the lower endpoint and the upper endpoint, whatever they are. That sounds incomplete because it's the proportion of all adults in the US who do what? It seems like there's a piece missing, and that's the specification part. We'll go through this for that example that we just had with smoking at least a pack a day, and we'll see how this works. These are the things we need to get the interpretation right. We need the confidence level, which for now is going to be 95%. We haven't done anything else. And that was what we computed, right? We did the 2 times standard error formula, and that's for 95% confidence. We got the endpoints already. They're 0.192 and 0.328. And then the tough part to get the parameter, the type of number is a proportion, right? It's a proportion, it's not a mean. The population would be all American cigarette smokers because the sample was 161 American cigarette smokers. And generally, if the sample is supposed to be just a little piece of the population, it seems pretty logical that that's what our population should be. And then the specification, the proportion of all American cigarette smokers who do what? Who smoke at least a pack a day. That phrasing, just about as it is, would give you the correct parameter. And there's the interpretation all put together. This is generally, I think, the easiest way to do it. So I've got the confidence level at the beginning, I've got the endpoints at the end, and I've got the parameter in between. And effectively, the way that I've got it phrased is that we're 95% confident that the parameter is in between the endpoints. If you took all the context out, that's what that says. It might be helpful, if you're not used to doing this, to go through it in kind of an itemized fashion like I did here to make sure that you get everything, especially with the parameter. The other parts aren't too bad. As far as the confidence level, the interval endpoints, nobody ever forgets the endpoints. The one thing I'll say about the confidence level, sometimes people use probability words there. I would stick with 95% confident. If you say 95% sure, I'll accept it because our book does, even though I think 95% confident is better. Make sure you don't say 95% chance. Anything that sounds like probability, that's bad. We're going to get to that very shortly in a few minutes. And as far as the parameter goes, the things that people tend to miss are the first 2. Most people don't forget the specification. If they make a mistake there, it's either they forget to put the type of number in, where it's just entirely missing, or they have the sample instead of the population. We'll get to that later, why that's bad. I can say it in a short fashion now, but we'll get to it again later. You don't want to have the sample instead of the population because you don't estimate a sample measure. There's no need to do that because if you have data from every individual in the sample, you could just compute the sample measure. You could compute p hat, you could compute x bar. That's not a thing that you estimate. Another example where we're going to compute the interval and then interpret the interval. So we have a random sample of 45 hotels. X bar, our sample mean of a cost per night of a hotel room in New York City is $306. And then we have a standard error of $11.50. So getting the interval won't be too bad. X bar plus or minus 2 times the standard error should do it. There's that. So 306 is X bar, 1150 is the standard error, so 306 plus or minus 23 will give us the endpoints of 283 and 329. Then the interpretation, so we need the confidence level, which is 95%. We need the endpoints, which are right there now in blue on the right side. And we need the parameter. What I want to point out here is that the parameter is actually in the second bullet point. It starts with the word average, and it's basically the rest of that sentence. Since the average is the type of number, hotel rooms in New York City would be your population, and cost per night would be the specification part. So everything's already there. The interpretation that I have just copies over that exact text. Since that work is already done, there's no reason to rephrase it or to redo it. And there's the full interpretation. So again, I've got the confidence level right at the beginning. I've got the endpoints at the end. And if you look at my parameter, it's identical to what's in that second bullet point. That's the easiest way to handle it. There's no reason to create extra work to do there. Here are some interpretations that don't work. The first one, the 95% confidence interval contains 95% of the data in the population. What's wrong with that? Well, it relates to individual values rather than a summary value, where a summary value would be a statistic that you would compute based on all of the individuals, like a proportion or a mean. this has to do with individual values, and that's not what a confidence interval is for. Further, it would be incorrect because there's a lot more variability between individual values than there would be between sample means or sample proportions. So what you would end up with is that a 95% confidence interval for mu, let's say, would actually contain far less than 95% of the data in the population. An incorrect application, but on top of that, it's also an incorrect statement. So the main thing with that first bullet point is make sure that it relates to a mean or a proportion, some kind of computation that you could do based on the sample rather than individual sample values. The second one, the problem there is that it relates to the sample, not the population. The sample mean is not a thing that you estimate because that would be something that you could compute. You could get the actual value for that. That's essentially an incorrect application there, where the thing that you want to estimate is a population measure because that's what's unknown. There's no reason to estimate a sample measure because you would have that exact value. So in that case, what you end up with for an interpretation is essentially a useless statement. You can create a confidence interval for that, but it's redundant when you have the actual value. The third bullet point, what's wrong with that is that it relates to probability. We haven't talked about probability yet at all, but there's a reason why this is wrong, which is that probability applies specifically to variables, and the parameter is not a variable, because if you go back about halfway through the section 3.2 notes, the parameter is a fixed quantity. And something that's a fixed quantity is not a variable. The idea of probability is not applicable. So the word probability is bad. Any word that implies probability, like chance, would also be bad. So just stay away from those things, and when you start off the interpretation, just start off saying that you're 95% confident that whatever. So 95% confident that the parameter is contained in the interval or is between the endpoints or something like that. And this is what we've got so far in picture form. We have our one sample that gives us the point estimate, which is the one that's in a slightly different color, the one that's in that sort of pinkish color. Then we have a bunch of other samples, those blue ones, which are how we get the sampling distribution, because once we have the sampling distribution, we can compute a standard error as the standard deviation of the sampling distribution. But when we get the standard error, then we can get a margin of error, and once we have that, we can get an interval. There's a big problem here, which is that in practice, you don't have a whole bunch of samples, you just have one sample. So it's like you have the pink one, but you don't have the blue ones. But if you don't have the blue ones, how do you get a sampling distribution? That seems like it's a big problem. It seems like it makes this whole thing fall apart. That's not entirely true. There is a workaround for this, but that's what we're going to cover in section 3.3.